we were just talking about ring activating and deactivating groups. And then these groups can also cause an effect where they direct the position of another thing that's being substituted. So substituents that are already on the ring determine the position that's taken by a new substituent. So what we find if we nitrate toluene, if we're adding nitrate to toluene, we find that 59% of it will be the ortho isomer, so in this 2 position, 37% of it will be the para isomer, and only 4% will be the meta isomer. And so it seems that having this methyl group here causes the nitro group to be added preferentially to either the ortho or the para position, and there's almost none of the meta that occurs. And this happens with other substituents as well. But if we take nitrobenzene and do the same reaction, we get almost exclusively the meta isomer. If we do this on toluene, we got ortho and para, and on the nitrobenzene, we get the meta isomer. And this pattern is followed for other electrophilic aromatic substitutions. If we were doing a chlorination of nitrobenzene, we'd get the meta isomer. And so there's a pattern here. So we say that these groups fall into one of 2 categories. They can be ortho-para directing or meta directing. So in this example, nitrate is a, lost my train of thought. It probably went off with the train. It's a meta directing substituent.
So if it was a different constituent on the top, like the CH3, it would have the same effect if you were adding a CH3?
What is affecting it is what was already present. So if we were adding some other substituent like chlorine or bromine or the sulfonic acid, the sulfonation, it would still go preferentially to the meta position if you're starting with the nitro group on there. And for toluene, whatever substitution reaction we are doing, we're going to get the ortho and para isomers. And it's because of this methyl group here. And we're going to look at why it does that. So let's look at this with toluene. So in the attack, in that electrophilic substitution, we get a carbocation being formed. If we get the attack in the ortho position, then we get the carbocation in the number 1 position, and then that can rotate around. Its resonance will be in the 1, I guess I tend to count clockwise. The 1, having trouble counting at all. The 3 and the 5 position, based on how those double bonds can move around with the resonance. And if it attacks in the para position, we have the cation, the carbocation being centered on the same carbon atoms. Do you see that? I'm not doing a very good job of explaining today. So we've got this carbon and this carbon and this carbon having the carbocation. And in the para position, it ends up being the same 3 carbon atoms. Well, this carbon is different than the other 2. This carbon is a secondary, would be a secondary carbocation because it's bonded to 2 carbons. And remember we said the more carbon atoms that carbocation is bonded to, the more friends it has to help it share its burden of the positive charge. So this tertiary carbocation is going to be more stable because this carbon has 1, 2, 3 carbons. So this is a tertiary carbocation. It's more stable. If we attack in the ortho or the para position, we can get that tertiary carbocation, which is more stable. So that's why the addition in this position of ortho or para is more likely to happen. If we attack in the meta position, we end up with the carbocation on this carbon, that carbon, or this other one, and those are all secondary carbons. So the carbocation here is less stable, and that's why for the methyl group, we get the ortho-para attack being preferential. Does that make sense? It's because of where the carbocation can be. This one in the box here, the blue dotted box, that's more stable, and this is more stable. And if the carbocation is more stable, that reaction is more likely to occur. So alkyl groups, we say, are ortho-para directing. And so the methyl group would do that, but any other alkyl group would as well, an ethyl group or a propyl group or anything like that. Those are ortho-para directing. Then there's a table in your book here. I've just put the top part of it. These are the excuse me, ortho-para directing groups. And if we look at the others, here's the alkyl groups, but if we look at the other ones, what they have in common is that all of them have lone pairs of electrons on the atom that is bonded to the ring. You see that? This amino group has got a lone pair, all of the variations of it. Hydroxyl groups, they've got lone pairs. The halo groups, they've all got lone pairs. These lone pairs help to stabilize a positive charge. So let's look at how that works. Here's the hydroxyl group. Looking at the same idea here, where we've got here bromination, the bromine attacking at the meta group, and we can get the positive, the carbocation here. When it's up here, there's additional resonance with the hydroxy group because this lone pair can come down in here and cause the positive charge to shift to the oxygen. The more you can spread out the positive charge, the more stable the carbocation will be. So this is more stable even than the tertiary carbocation we saw for the alkyl groups. And then, of course, it can also be on these other two secondary carbons. The same thing will happen with the para attack. That carbocation can be in one of three places, and when it's up here, it can go additionally to the oxygen. So these in the box are additionally stable. In the meta attack, we don't get that additional stabilization. We get just the regular resonance, but no effect of a tertiary carbon or the additional resonance with that oxygen. Does that make sense? Yes?
So the meta, they're all stable or they're all not stable?
These are not as stable. So you will get a small amount of meta product being formed. In the example that we showed, it was 4%. So there's a little bit that will happen, but not very much. Because the carbocation has to be around long enough to react and form the substituted benzene. It has to stick around long enough for this hydrogen to come off. And this is so unstable that it doesn't work very well. So the generalization is that groups with unshared electrons on the atom that's attached to the ring are ortho-para directing because they stabilize the cation. Meta-directing groups, what we see with these is that the atom bonded directly to the aromatic ring is either positively charged or it's part of a multiple bond to a more electronegative element. So these are the meta-directing groups. Here on this nitro group, this carbon actually has a +1 formal charge. On here, the carbon is bonded to nitrogen with multiple bonds, and so that withdraws electron density. And all of these, here's sulfur, all of these, the atom that's bonded to the ring has multiple bonds and it's bonded to more electronegative elements. And so they withdraw electron density from that atom. And so it's not able to help stabilize the carbocation. Oh, I thought there was another picture, there isn't. So what these do is these have the opposite effect of an atom with unshared electrons. So if we go back to this picture here, the oxygen with its lone pair of electrons here stabilized this carbocation and made the ortho and the para more likely to occur. When we have a positive, like with the nitrogen and a positive formal charge here, that destabilizes this carbocation and makes the ortho and para less likely to occur, and then the meta occurs. So this is the explanation behind why they are. I don't expect you to be able to spit back the explanation to me. It can be helpful, though, in trying to remember. And you do need to know which of these are ortho-para-directing and which are meta-directing. So the division here is that the ones with lone pairs and just the plain old alkyl groups, no double bonds, these are ortho-para-directing. The meta-directing ones have multiple bonds to electronegative elements. So we've got oxygens and nitrogens bonded with multiple bonds to the atom. And those are the meta-directors. Any questions?
Can you say that again?
Yeah. So the meta-directors, what they have in common is that there will be multiple bonds to an electronegative element. So here we have double bonds to oxygen, here double bond to oxygen, here double bond to oxygen. This is a triple bond to nitrogen, which is more electronegative than carbon, and this one has a double bond to oxygen. Those are the meta-directors. The double bond prevents the electron withdrawing effects destabilize that carbocation. The ortho-para-directors, the alkyl group, you just kind of have to memorize that one. But the rest of these all have lone pairs on the atom that's bonded to the ring. And that's not the case for the meta-directors. So ortho and para, alkyl groups, and lone pairs. Meta-directors, multiple bonds to electronegative elements. The substituents can also affect the rate of substitution. All of those meta-directing groups are deactivating. We looked at this a little bit on Tuesday. They're deactivating. They cause the rate to be slower than just benzene because they destabilize that carbocation. Most of the ortho-para-directing groups are activating, except for the halogens. The halogens are deactivating because they're strongly electron withdrawing. So the halogens have this kind of opposite effect. They're ortho-para-directing because they have these lone pairs that can stabilize the carbocation, but because they're also strongly electron withdrawing, they deactivate. So here's the whole table. So if we're looking on the left, ortho-para-directing is all of these guys in the blue. And down here in the, I guess it's violet. Well, it's violet on my screen. It's more brown here. These are all meta-directors. On the other side, we're showing activating and deactivating. And the halogens are deactivating. So for that, they're lumped in with these guys. But they're not meta-directors, they're ortho-para-directors. If I was making this up, I would make it more straightforward. It's a lot of stuff to cram into your brain. You have my sympathies. I have a hard time remembering some of it myself. Any questions? The directing effects can be very important when you're synthesizing compounds. So if you have a multi-step synthesis, we have to consider the directing and activating effects of the groups involved. So in this instance, doing the same two reactions, we're going to get two different products. So here's benzene, first doing a bromination, we're going to get bromine on here. Bromine is a halogen. Is that a meta-director or an ortho-para-director?
Ortho.
It's an ortho-para-director because it's got lone pairs. If we do the Lewis structure for bromine, it's got 3 lone pairs on here. So we're going to get ortho, when we do a nitration, we're going to get ortho, bromo, nitro, and para. We're going to get ortho and para. If we do it in the reverse order and do the nitration first, this nitro group is meta-directing. And so then when we add the bromine, we get the meta. And so by doing these in a specific order, we can tailor what sort of product we're going to end up with. So we need to be aware of it in this class, but we're not going to do very much with it. In the full-blown 2-semester organic chemistry class, they ask you to, write out a step-by-step synthesis to make this thing, and you have to put all these things together. And it's, once you get all the stuff crammed into your brain, it's kind of fun because it's like a puzzle. Well, if I do this, then this happens, but that's not what I want, so then I have to go back and do this other thing first, and it gets to be this interesting puzzle. But we're just going to tell you about it. And this last section about the polycyclic aromatic hydrocarbons, I'd like you to read this section and just be aware of what the polycyclic aromatic hydrocarbons are, but that's about all we're going to do with it.